So before we go any further, let's talk about some of the vocabulary involved with graph theory. So first off, a vertex. So a vertex is each of these things. It is the dots, the locations where edges meet. So this might be where two streets meet, like an intersection. It might be, like in our bridges example, it might be representing a city or a location, and then these edges, those are the lines connecting the vertices. Those are my edges. Those can represent some kind of connection. So they might be a physical connection like this, or you could have like two cities, like Seattle and LA, and an edge connecting them could represent something like a flight path. So an edge is simply representing that there is a connection between those two locations or those two vertices in some way. So degree of a vertex talks about how many edges meet at the vertex. So if I have a vertex all by itself, this would be degree 0. If I have one edge coming out of that vertex, then it would be degree 1. If I have two edges coming out, it's degree 2. If I have three edges meeting at a vertex, it's degree 3. So degrees tells us how many edges meet at a vertex. So what's the degree of this vertex? There are 1, 2, 3 edges meeting at that vertex, so it's degree 3. How about this one? There are 1, 2, 3, 4 edges meeting at that vertex, so it's degree 4. This one is degree 2. So now, path. So on a graph, we can talk about routes from one location to another. So a path is a route along our graph that starts and ends at different locations. So for example, if I start here and walk this way, this way, this way, this way, this way, that way, that way, this is a path. A path on the graph. A circuit, on the other hand, is a path that returns to the starting point. So the circuit has to be looped around. So if I start here, this would be a circuit. Likewise, we could start here and go here, 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 here. Uh-oh, no, never mind on that one. Here. And we've got ourselves another circuit. So it's possible to have multiple circuits on a graph, though later we'll talk about the idea of covering all the edges with a circuit, but that's a different problem, so we're not quite there yet. So next idea is an idea called connected. In this case, this graph is connected. The reason is because if I pick any two vertices, there is a path that will get me from here to here. I can simply follow this path there. In contrast, consider a graph like this, right, where we have 3 vertices over here and 4 vertices over here, and if I were to pick this vertex and this vertex, there is no way to get between those two vertices, and so this is not connected. And in most of what we're going to be doing in this class, we'll be looking at connected graphs, but certainly we need to consider not connected graphs. So lastly is the idea of weights. Now, sometimes all we care about is the fact that there is a connection between two locations, like with our bridges. But in a case like walking these paths, we might be interested in the length of these paths, in which case we might say that this is 100 feet, and this is 200 feet. And those would be weights, or a length or a cost associated with the edge. In case of our flight path here, there might be a flight cost that would be associated with that path, and that would be the weight on that edge. So here's a portion of a housing development from Missoula, Montana. And as a part of her job, the development's lawn inspector has to walk down every street in the development, making sure that homeowners' lawns conforms to the community recommendations. Now, you can sort of understand that if she has to do all this walking, she's going to want to figure out how to walk as little as possible, ideally being able to walk the entire development without having to backtrack along any streets. So if we're going to analyze this and start looking at it mathematically, looking at this big, huge picture here is pretty complicated, and so we might try sort of simplifying things. And one way to do that is to say, let's identify sort of junction points. So let's identify places where streets meet, or sort of where there's a corner. And so we're going to define all these points where it looks like streets meet. And we're going to call those points vertices of what's going to be called a graph. Now, this is not graphs like your y equals x squared graphs from algebra. This is graphs as in a graphical representation of the situation. So we introduce these vertices to represent the intersections, and then we're going to add some edges now to represent the streets themselves. So along each of these streets, we're going to draw an edge. And when we put this all together, we get a graph. This graph represents the city. Sort of taking away the back picture now, we would get something that looks like this. And here is a set of vertices connected by edges, and this defines a graph. The idea here is that we're simplifying the problem down from this sort of complicated picture to just the important things, the junction points and the edges themselves. And it's interesting to note that the specific layout here is not highly important. Really, it's just the connection and the length of those edges that matters. So for another example of sort of how graphs come into things, consider this. Back in the 18th century, there was a Prussian city called Königsberg, where a river, you can see here, ran through the city. The river forks, and there were 7 bridges that connected, that crossed the various forks of the river. And as a weekend amusement, people would see if they could find a route that would take them across every bridge once, and then return them to where they started. And Leonhard Euler was sort of the father of this branch of mathematics called graph theory, and he analyzed this problem, and kind of like we're doing, introduced a graph into this situation. So let's see if we can do that here. So really, what's important? What we really care about is the bridges. If I start here and, if I start here and walk across this bridge, and then I'm going to walk across this bridge, I don't really care how far I have to walk here. That's not relevant to this question, right? All that matters is that I went from this island to this side, and then maybe walked back across this bridge to, really, we walked back to this side of the, go back to the island. And then if I walk across this bridge, and then walk back across to the island, I'm really treating all of this island as one location. So really, we have sort of the whole north bank area up here. We have our island here, and we have our whole south bank here, and our whole sort of east bank over here. And we have 2 bridges connecting the north bank to the island, 2 bridges connecting the south bank to the island, 1 bridge connecting the island to the east bank, 1 bridge connecting the north bank to the east bank, and 1 bridge connecting the east bank to the south bank. And this picture starts getting at sort of the core notion, but again, it doesn't really matter where in the north bank we are. So what we could do is shrink this entire north bank down to a single vertex. And the island could be represented by a single vertex, and the south bank can be represented by a single vertex, and the east bank can be represented by a single vertex. And there are 2 routes to get from the north bank to the island, 2 routes to get from the south bank to the island, 1 route here, 1 route here, and 1 route here. And so here is a simplified graph that represents this scenario. And by looking at this graph, it makes it a little easier to look at the question of, is it possible to walk over every bridge? In this case, that would mean crossing over every edge once, and return to your starting location. In other words, return to your starting vertex. So suppose we want to travel from Tacoma over here to Yakima over here, and there's a few routes we can take, either down through Eatonville and Packwood, or through Auburn and North Bend, or through Auburn and Mount Rainier. And it's not quite clear which route is fastest. And so we're going to use something called Dijkstra's algorithm, which solves this, what's called the shortest path problem. So we're going to start by saying, we're going to start by looking at our ending vertex and saying, I know that this vertex is 0 miles from the end. Why? Because it is the end. And so next we're going to look at all the vertices that lead to Yakima. So for each of these, we're going to figure out how far it is from the end. So this one is 104 miles from the end. This one is 96 miles from the end. This one is 76 miles from the end. And now, that's sort of our first step. So next thing we're going to do is we're going to identify our next current vertex. So we go to the vertex that is the closest to the end. So we're going to identify the vertex that has the smallest distance. That's this one. We're going to identify it as current. And so now from that vertex, we're going to work backwards and say what vertices lead to this one. So going this way, we say 76 plus 96 is 172. And then we say 76 plus 27, let's hear, 76 plus 27 is 103. But 103 is longer than 96, and so we're not going to record that one, because that one doesn't help us any. Remember, we're trying to get shortest distances. And so it's shorter to go directly from Mount Rainier to Yakima than to go from Mount Rainier to Packwood to Yakima, right? That was what that 103 told us, is that the combined length here is 103, and that's longer, so we don't want it. Okay, so now that we're done with that vertex, we mark our next vertex, our next shortest vertex, as current. And we work backwards from there. So we say the only leading thing leading to there is this edge here. So we work backwards. 96 here plus another 79 here gives me a time of, let's see here, 175 for that one. Okay, and that was the only edge leading in, so now we're done with that one, and we'll move on to our next shortest edge here and work backwards. So notice now that working backwards from here, this distance is 104, this time, I guess these are times. Anyway, this time is 36, and 36 plus 104, right? 104 minutes here, 36 minutes there, is a total of 140. And 140 is shorter than 175. So we're going to replace that 175 with 140, because that was a shorter path, and we were looking for the shortest path here. So now all three of these vertices we've already looked at. So now we move to the next vertex that is shortest, and that is this one. From here, again, we work backwards. So 140 plus 20 is 160. And now we're done with that vertex. We come down here. 172 plus 57 is, I don't know what it is, but it's certainly bigger than 160, and so we don't care. And so we have found our shortest path. Our shortest path has a total travel time of 160, and it looks like it routes through Auburn, through North Bend, down to Yakima. And so that is the shortest path found through Dijkstra's algorithm. So a shipping company needs to route a package from Washington, D.C. to San Diego. To minimize costs, the package will be first sent to their processing center in Baltimore, Maryland, then sent as part of mass shipments between their various processing centers, ending up in their processing center in Bakersfield, California, and there it'll be put on a small truck out to San Diego. So we're mainly routing here between these processing centers, and so we calculate the travel time, we add a few hours for processing, and we end up with a table of values that looks like this. And so this is the city at each point here. Like, this is the time from Baltimore to Chicago would be 15 hours. The time from Baltimore to Atlanta is 14. If there's no value there, that means there's no connection between those cities. So one option here would be to draw a graph. So we could actually draw out Bakersfield, Atlanta, Chicago, and draw the connections and work off of it that way. But let's see if we can work directly off the table. So we're going to start in Bakersfield because it's our end position. Remember, we're going from Baltimore to Bakersfield, and so we mark it as having a distance of 0 from the end. So it's our current vertex, so we're going to go backwards from there and say, from there, Denver is 19 minutes away, sorry, hours away, and Dallas is 25 hours away. Okay, so now we're done with Bakersfield, and we move on to the next closest city, which is Denver. So from Denver, we work backwards again. So from Denver, we could go, let's see, we could go 18 minutes additional to Chicago, and so 19 hours plus another 18 hours would be 37 hours to Chicago. Or from Denver, we could go to Atlanta, and 19 plus 24 hours would be 43 hours to Atlanta. Or we could go back to Bakersfield, but why would we go back to Bakersfield? So we're not going to do that. So at this point, we're done with Denver, and we move on to the next shortest city, next closest city. So that would be Dallas. So we'll move on to Dallas, and from Dallas, we can figure out what's going on. So from Dallas, 25 plus 18 here. 25 plus 18 would be 43 to Chicago, but 43 is longer than our current path. We could also say 25 from Dallas, we could go to Atlanta, and Dallas to Atlanta would be 25 plus 15 is 40, and 40 is better than 43, so we're going to replace that 43 with a time of 40, because we have a more efficient route now. Okay, and of course we don't want to go back to Bakersfield, because that's where we're, that's sort of where we're working back from. And so we're now done with Dallas. So our next shortest is Chicago, and so marking Chicago as current, we say, let's see here, I could go to Baltimore, so 37 here plus, let's see here, 37 here plus 15 there would give me a time of 52 to Baltimore, routing through Chicago. We could also say 37 plus 18, but 37 plus 18 is going to be much bigger than 19, so we don't want that. 37 plus 18 to get to Dallas is definitely going to be bigger than 25, so we don't want that one. 37 plus 14 is going to be bigger than 40, so we don't want that one. And so we're completely done updating for Chicago now. And we move on to the next closest city here. So from Atlanta, we could go to Baltimore, which should be 40 plus 14, but 40 plus 14 is 54, which is longer than that route. And so we definitely do not want to do that. We also don't want to go back to Denver, Dallas, or Chicago, and so we are now done with that. And so now we know the shortest route from from Baltimore to Bakersfield here is going to have a total time of 52 hours. So we want to find an Euler path on this graph. Now, an Euler path is a path, and remember, a path means that it goes from one point to another, not necessarily returning to the same point. So it's a path that uses every edge once and only once, so no repeats. Now, we're allowed to visit the same vertex multiple times with Euler paths, but not the same edge. So for example, if I started here, I could go this way. And let's say that's step 1. And then I could go here. That's 2. And I could go here, and that's 3. And I could go here, and that's 4, but now I'm stuck because I can't go anywhere, and I haven't visited every edge yet. And so this was not a particularly good attempt at finding an Euler path. This is not an Euler path. So let's try again. Maybe I will start instead over here, and then I could go 1, 2, 3, 4, 5. And notice now I have covered every single edge of the graph without repeating any of them. Notice though I started here and I ended over here, so I have not returned to my starting point. This would be an Euler path. So now we want to find an Euler circuit on the graph before. So an Euler circuit is very similar to an Euler path, except that we must return to the same vertex because it is a circuit. So again, the idea is we're going to visit every edge once with no repeats. And this time, because it's a circuit, we need to return to the starting point. Okay, so let's say we start, I don't know, how about here? And so let's do 1, maybe 2, 3, 4. Remember, it's okay to visit the same vertex with an Euler circuit, just not the same edge. 5, 6, 7, 8, and 9. And look, we did it. So we have visited every edge exactly once, and returned to our starting point. Now, interestingly, this type of drawing is also sometimes called a unicursal drawing, because you can draw the entire thing without lifting your pen, right? If I had started over here, I could draw this entire circuit without lifting my pen once, and that's one of the features of an Euler circuit. So suppose we got a graph here and we're wondering, does this graph have an Euler path? How about an Euler circuit? Well, it turns out that there's a really easy way to tell, and it comes down to the degree of the vertices. And so it turns out that in order to have an Euler circuit, all vertices must have even degree. Even being like 2, 4, 6, 8, right? Even numbered degrees. And the idea is really simple, that the idea is we need to make it so that every time we come into a vertex, we have a way out. So if I have another way in, I need another way out. And so we need even degrees on all of our vertices. For an Euler path, it's similar, except we can have either 0 or 2 odd degree vertices. Otherwise, all the rest must be even degree for the same reason. Now, the reason it's okay to have 2 odd degree vertices is because with an Euler path, we don't have to get back to our starting point. So here, notice that this vertex has degree 2, this vertex has degree 3, this one has degree 1, 2, 3, 4, this one has degree 1, and this one has degree 4. And so we have one pair of vertices, so 2 vertices with odd degree, and that'll be okay. What it means is that our Euler path is going to have to start and end at those vertices. So let's see if we can come up with an Euler path here. So I could come down here, I could come up here, over here, up here, down here, back up here, and down there. And there we go. There's my Euler path, starting here and ending at that vertex. Right? Notice there would be no way to do an Euler circuit here. So let's take a look at another one. Does this graph have an Euler path? How about an Euler circuit? Well, let's see. How many odd degree vertices are there? 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, uh-oh. So in this graph, we have a ton of vertices with odd degree. And so there is not going to be possible to come up with a Euler path or an Euler circuit on this graph as drawn. Now, that's for this particular problem, which was, for our lawn inspector who was walking along these paths. Now, if, on the other hand, let's say it's snowing and we got a snowplow that has to go down every street, but the street is wide enough that it has to drive down twice, then our graph would look more like this, where each edge is going to be driven over twice. Now, if we look at this graph, you can see that every vertex is even degree, and so this graph will indeed have an Euler circuit, because every vertex has even degree. So the snowplow would have a route where it could drive over every street twice, right? Once in one direction, once in the other direction. It could drive over every street twice, and get back to the starting point. So now that we've talked about Euler circuits, let's return back to this bridges problem, because if you'll notice, the idea was the townsfolk folks would see if they could find a route that would take them across every bridge once and return them to where they started. And if you remember, we represented this as a graph by introducing a vertex for each of the land masses, and then an edge for each of the bridges that could be taken to walk from one land area to another. And so our graph ends up looking like, you can really see it over there, but in case if you're having trouble, looks like this. And so the question we could ask is it possible to find a route that would take them across every bridge once and return them to where they started? And you'll notice that if we look at the degree of these vertices, we have degree 1, 2, 3, degree 1, 2, 3, 4, 5, degree 1, 2, 3, and degree 1, 2, 3. So it turns out that no, there is not an Euler circuit for this bridges scenario, for the bridges of Kruskal, and in fact, there's not even an Euler path, right? Because we have all of our vertices here have odd degree. It's more than just a pair, and so there's no way to even start in one location, cross every bridge once, and end up in a different place. There's no way to cross every bridge once without visiting, without having to cross a bridge twice. So let's find an Euler circuit on this graph. We can tell from all the even degrees that it's gonna have an Euler circuit. Now, most of the time, it's gonna be easiest to just guess and check at an Euler circuit. But if we want a more sort of formulaic approach here, we use something called Fleury's algorithm. The way it works is we pick sort of a starting point. So we just pick any old vertex that we want to start at, and we choose one of the edges that is leaving our current vertex. And we can pick any edge we want as long as it doesn't separate or disconnect the graph. So let's say we pick A as our starting point here, and the edge that we choose is A to D. So A to D is not going to disconnect the graph, so we'll go ahead and add that in as our first step. Now over here, in sort of our duplicate copy here, we're going to delete that edge. So we're going to delete that edge because we feel like it. So then, from D, we're going to look in these two edges and say, which one do I want to go to next? Now, we'd want to be careful here. We would not want to remove or choose edge D to C, because notice if we choose D to C, it's going to disconnect the graph. A and C will no longer be connected to the rest of the graph. So instead, maybe let's choose D to E. We'll choose that as our second edge, and we'll delete that. So now we're here at E, and we choose an edge that we want to follow. In this case, because we've deleted these edges, that's preventing backtracking. There's only one route we can take now, and that is to B. And then from B, there's only one route we can follow, and that's to D. And then from D, there's only one route we can follow to C. And from C, there's only one route we can follow back to A. And there is our Euler circuit. Now, depending upon how we had made our original choices at the beginning, we may have ended up with different Euler circuits. For most graphs, there is not just one Euler circuit. If there is an Euler circuit, there's usually not just one, but multiple Euler circuits, depending upon sort of the choice of what direction you go first. So for the graph here, let's find an Eulerization. So the idea behind Eulerization is that right now this graph does not have an Euler circuit. Why? It doesn't have an Euler circuit because there are 1, 2, 3, 4, 5, 6 different vertices, all that have odd degree. And so there's no way that we can do an Euler circuit on this graph, right? There's no way we can walk this graph without backtracking. And so to address that, because, if let's say we were actually planning a route on this graph, we'd have to backtrack, now we know. We want to sort of figure out how to do that in the best way possible. And so what we're going to do is Eulerize the graph. That means we're going to duplicate edges until it will have an Euler circuit on it. Now we're going to duplicate edges like this to indicate that I'm going to walk this edge twice. I'm going to walk it once this way and then probably once the other way. We don't want to create new edges, so we don't want to do stuff like this. Think about what this would mean in terms of like city streets. This would mean creating a new street between these two intersections, and that doesn't really make any sense. It makes sense, though, to walk an edge twice, right? To walk along the street twice. And so in order for this to become Eulerized, in order for it to have an Euler circuit, each vertex is going to have even degree. Right now, this vertex has degree 3, which is odd. But if I were to add a duplicated edge here, now it has degree 4. Right? 1, 2, 3, 4. Likewise, this one now has degree 4. This one has degree 4. This one has degree 4. Now I just need these two to both have degree 4. And there's no direct way to connect them. So our only option is to make hops. Like that. So notice now, this edge has degree 1, 2, 3, 4. This vertex, which previously had degree 4, now has degree 1, 2, 3, 4, 5, 6. It's still even, so that's okay, right? And this vertex has degree 6, this one has degree 4. Now this graph is Eulerized. Now we can find an Euler circuit on this graph with the added or duplicated edges. Now it's important to notice here that this is not the only Eulerization that we could have done. We also could have duplicated, say, this edge and this edge, and this edge and this edge, and that edge. And this would have also created an Eulerization. This one turns out to be the same number of duplications as our previous one. But if we had instead done something like this, this is more duplicated edges. In general, we want to minimize the number of duplications we have in our graph, because each of those duplications means that we're walking along an edge twice. And generally, that's not a good thing. So let's look at another graph. All the odd degree vertices are highlighted here. Let's see if we can find an Eulerization of this graph. So you may have noticed that the pattern is that we're going to connect vertices with odd degree. And so this vertex here, I can either duplicate here and here, or duplicate here and here. And I don't think it really matters, so I'll duplicate here and here. Both of these vertices now have even degree. So now this one's odd and this one's odd. So if I duplicate there, both of those now have even degree. If I duplicate here and here, both of these now have even degree. And duplicating here and here, both of those now have even degree. And so we find that for our lawn inspector, if you remember this graph, that in order to walk this entire neighborhood, she would have to backtrack 1, 2, 3, 4, 5 times in order to cover the entire area and get back to her starting point. Now, it's not clear whether this is the most efficient Eulerization, but it's certainly an Eulerization that looks pretty good. So here we want to find a Hamiltonian circuit for this graph. Now a Hamiltonian circuit is first and foremost a circuit, right? Which remember means that it's a path that returns to the starting point. Returns to the starting point. Now, you might remember an Euler circuit was one that covered every edge exactly once, and we didn't care about the vertices. Hamiltonian circuit is different. In this case, we want to visit every vertex. Once with no repeats. Now, because all we care about is the vertices, it doesn't matter whether we visit all the edges. So if I start here, I could draw my path this way, and then maybe this way, and this way, and this way. Here, 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 here. Now notice I would not want to go back up because I've already visited this vertex and I don't need to visit it again. So I'll just continue on. And there we go. There is a Hamiltonian circuit on this graph. It visits every vertex exactly once with no repeats. And again, it doesn't matter that we haven't visited all the edges. All we care about is the vertices. Let's look at another one. So does a Hamiltonian path or circuit exist on the graph below? So in this case, there is no way to find a Hamiltonian circuit. And that's pretty clear because if I start at vertex E here and come down to, well, let me draw that a little better, and we come down to C, then there's no way for me to get back to my starting point without visiting vertex C again. So if I come out here, and I go here, and I go here, and now I want to get back to E, the only way to get there is to go back to C, and that's bad. So there's no Hamiltonian circuit. Now, a Hamiltonian path visits every vertex exactly once, but doesn't have to return to the same starting point. And yes, we do have a Hamiltonian path here. We could go this way, this way, this way, this way, and now I have visited every vertex exactly once. And so this is a Hamiltonian path. Now, most of the time we're going to be interested in Hamiltonian circuits, not the Hamiltonian paths, but this has one nonetheless. So when we have a graph with weights on the edges, so here we have weights, so to travel from A to D has a cost of 1. This might be $1, it might be 1 mile. Somehow this is representing the cost or expense of traveling from vertex A to vertex D. So in this case, there are a lot of different Hamiltonian circuits on this graph. We're interested in the minimum cost Hamiltonian circuit, and sometimes this is called the traveling salesman problem. And the reason is, you can imagine that you have a salesman who needs to visit these 4 different cities and wants, they have to visit every single one of them, but they don't want to have to backtrack. So they want to visit each city and then return home at the end of the day. Okay, so we're going to apply an approach called the brute force method, which does exactly what it sounds like. We're just going to try every single possibility. So let's try a few possibilities here. So one possibility would be to go from A to B to C to D to A. So that was A, B, C, D, A. Right? A, B, C, D, A. So this lists the order in which we're visiting the vertices. And the total cost here would be 4 plus 13 plus 8 plus 1. Right? We add up the cost of each of those legs of our path, and we add those up, and we get a total weight of, or total cost of 26. Now notice that this is exactly identical to the circuit ADCBA in terms of cost, right? ADCBA. It's just the reverse order. And so we're not going to look at both of these because we know that they're going to have the same cost. So we don't consider these to be unique circuits. And so we're just going to ignore that one. And now let's look at another possibility. So another possibility would be to go from A to B to D, and from D down to C, back up to A. So that was A, B, D, C, A. And that would be 4 and 9 and 8 and 2, and that has a cost of 23. Now I'm going to get those out of the way because that's starting to get a little messy here. And let's look at one more. There's one more unique circuit here, and that's A, C, B, D, A, right? This is different than our first one. The first one we went A to B. So this was A, C, B, D, A. So that's 2 and 13 and 9 and 1 has a cost of 25. And so of these 3 unique circuits, and it turns out that these are all the unique circuits, the one that is minimum cost is this one right here. So this is our minimum cost Hamiltonian circuit for this particular graph. And here was what we called the brute force method, right? We looked at every single possibility, and while this will always give us the ideal, the optimal answer, so this is called an efficient algorithm, an optimal algorithm. It is not an efficient algorithm. So this is optimal because it will always give us the right answer, the best answer, but it is not efficient. And we'll see why in just a second. So to see why brute force is not an efficient method, consider the question of how many circuits would a complete graph with 8 vertices have? So now a complete graph means that every vertex is connected to every other. So there's 1, 2, 3, 4, 5, 6, 7, 8 vertices. And so a complete graph means each vertex is connected to every other vertex. And I'm going to get tired of drawing this pretty quickly, so you can just imagine the rest of it. So let's think about how many circuits there would be. So let's say I'm sitting here at my starting point. How many different places can I go to from here? So from here, I can go to any of 7 different locations. So I have 7 choices for my very first visit, right? So from my starting point, I can go any of 1, 2, 3, 4, 5, 6, 7 different directions, right? Now from each of those, so let's say I decide to go here. From there, how many choices do I have? Well, this vertex is connected to every other, because it's a complete graph. I've already visited this city, so I don't want to go there. So I have not 7 choices, but 6 choices for my next one. And I'm going to multiply those, and let me show you why. So let's say I went here. From here, I have 1, 2, 3, 4, 5, 6 different choices. If instead I had gone here, I would have had 1, 2, 3, 4, 5, 6 different choices. If I went here, I would have had 1, 2, 3, 4, 5, 6 different choices. So notice for each of those 7 original branches, I'm going to have 6 new possibilities, and so that's 7 times 6, right? 6 for each of those 7 would be 7 times 6. Now let's say I pick one of those, and now how many choices do I have for my next route? For my next path, I've got 5. For the next one, 4. For the next one, 3. For the next one, 2. And for the last choice, there's only 1, right? Once I've visited every other city, there's only 1 choice to get back to the starting point. Now, it turns out that this is going to be twice as many as there actually are of unique circuits. The reason is because the circuit that I end up with here is identical to the circuit in reverse order. And so I'm actually going to have to divide this by 2 in order to get the true number of unique circuits. And this number ends up coming out to be 5,040 unique circuits. Now, that is a lot of circuits, and I certainly don't want to have to list all 5,000 of them and calculate the weight of each of them. That is pretty darn tedious. By the way, there is a handy notation for this called a factorial. This would be n minus 1 over 2. Sorry, n minus 1 factorial over 2, where n is the number of vertices. If you've never seen this before, the idea of a factorial is that, for example, let's see, so like 3 factorial means 3 times 2 times 1. 5 factorial means 5 times 4 times 3 times 2 times 1. So in this case, this would be 8 minus 1 factorial over 2, which means that's 7, right? 7 factorial, which means 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 2, which you'll recognize is exactly what we had there. And if your calculator happens to have that factorial button, it can come in handy. So there we go. It turns out that we have all these crazy number of circuits possible, and while 5,000 would be ridiculous to do by hand, a computer could do that pretty easily. But if we go and start adding more cities to our visit, you can see that very quickly, like 20 here, with only 20 cities, we're already up to this ridiculously huge number of cities. I mean, this would take a computer doing 1 billion circuits a second, over 2 years, about 2 years, to look at all of these. So it turns out that using brute force is not going to be a reasonable method for graphs with more than maybe 3 or 4 vertices. So instead, we're going to look at some alternate methods called heuristic methods. So to approach our traveling salesman problem, we're going to use what's called a heuristic algorithm. Now, this is one that is not optimal. So this is not optimal, which means sometimes it doesn't give us the best answer. But hopefully it gives us a better answer than just randomly guessing. So we're going to go ahead and give this a try here. So the way the nearest neighbor algorithm works, and this is our first heuristic, is we pick a starting point. So let's go ahead and use A as our starting point. At every point along the way, we move to the nearest or cheapest next unvisited vertex. So we're going to look and say, what are my choices? I can either go to B, to D, or to C. This path has a cost of 4, this path has a cost of 1, this path has a cost of 2. I like cheap, and so I'm going to go this way down to D. So I'm taking the cheapest route. Now notice this is what's called a greedy algorithm. We're always taking the cheapest route that we can find. So now from D, I look at my options, either 9 or 8. I don't want to go backwards, right? So we're going to ignore the already visited vertices. And here this 8 is my cheapest path. So now my options are either, well, I really only have one option because I don't want to go back to the beginning yet because I need to visit every vertex. So my only option now is to go over here, and then to get back to the start, my only option is to go that way. And we ended up with the circuit ADCBA. ADCBA, right? And the total cost there is what? 1 plus 8 plus 13 plus 4 is 26. Wow, that was like the worst circuit in the graph. So it turns out that, like I mentioned, nearest neighbor algorithm is not always optimal. And here's a case where it certainly gave us a non-optimal result. So suppose that we have a salesperson who needs to travel to Seattle, LA, Chicago, Atlanta, and Dallas on business, and figures he'll just go to each of the cities and return home, and wants to minimize the the travel cost. And so we looked at some travel flight costs here, some flight costs, and let's see if we can find a pretty good, at least, circuit using the nearest neighbor algorithm. So starting here in Seattle, we say, what is my cheapest option? So we got 70, 145, 140, 120, so it looks like 70 is our best option. So we got Seattle, so far we got Seattle to LA. And then from LA we've got, looks like the cheapest option, 100, 170, 150 is 100. So to Chicago. Got some good travel deals here. And then from Chicago, we can go 140. Oh, no, we don't want to go back home yet, right? We still need to visit Dallas and Atlanta. So we only really look at the next, the unvisited cities. So of those two, it looks like Atlanta is the cheapest. So we'll go to Atlanta next. Atlanta. And then we really only have one option at this point, and that's to go to Dallas because it's our only unvisited city. and that will return us home to, from there we'll return home to Seattle, and that completes our circuit. So now we visited every city. Total cost here, if we add these up, I think is $450, which is insanely cheap. And there is our circuit generated using the nearest neighbor algorithm. So here we have a big old table of travel distances between some cities in Oregon. And so, for example, here Ashland to Astoria is 374 miles, and we also see that here, Ashland to Astoria. So everything is mirrored, shows up in the table twice. And so let's see if we can find an efficient circuit between these cities using the nearest neighbor algorithm. And we're going to start in Portland. So I'm going to jump as we go between this graph of those cities and our table here. You don't really need to create a graph necessarily, but it can be helpful to sort of visualize what's going on. So let's start in Portland. So starting in Portland, we look and say, what is our cheapest destination, the quickest place we can go to? Because remember, nearest neighbor, we always go to the nearest location. And so that is 47, going from Portland to Salem. So we're going to go from Portland to Salem, which takes 47, which is 47 miles. So now we are in Salem. So from Salem, where should we go? So my nearest neighbor to Salem is Corvallis, which is 40 miles away. So from Salem, we're going to go to Corvallis, which is 40. Notice that my graph here has absolutely no relation to their physical locations of these cities. I just listed them all in a big circle so that I could easily draw my graph here. So now we're in Corvallis. And from Corvallis, I'm going to say, where do I want to go next? I'd really love to go to, wait, we just came from Salem, never mind. I'd really love to go to Eugene, because Eugene is next closest. So from Corvallis, we're going to go to Eugene, which had a distance of, Corvallis, Eugene, 47. Yes, 47. 47. Okay, so now we are in Eugene. So from Eugene, I'd really love to go to Salem. Oh wait, we've already been to Salem, so no Salem. I'd really love to go to Newport. Great, Newport is our next cheapest. So from Eugene, we're going to go to Newport, which was 91 miles away. Okay, so from Newport now, we're going to go to, let's see, from Newport, we've already been to Corvallis, we've already been to Eugene, we've already been to Portland, we've already been to Salem. You know, just for simplicity here, let's do a better job of keeping track of this. We've already been to Corvallis, we've already been to Eugene, we've already been to Newport, we've already been to Portland, we've already been to Salem. Great, now I know I'm not going to visit any of those again. So right now I'm in Newport, right. So I'm in Newport, and of my remaining choices, the cheapest is Seaside, 117. Okay, so Seaside, 117. Excellent, Seaside, 117. So now Seaside is visited, I'm in Seaside. So from Seaside, there I'm going to Astoria. Astoria is close, so I'm going to go to Astoria, which is only 17 miles away. So now I have visited Astoria, and from Astoria, I'm going to go to, apparently I'm going a long ways, I'm going to Bend, Oregon. So from Astoria, I'm going to go to Bend, which was a whopping 255 miles away. Okay, now I'm in Bend. So from Bend, my next choice is Ashland, which is 200 miles away. So from Bend, I'm going to go to Ashland, which was 200 miles away. And then from Ashland, I'm going to go to, I don't have a lot of choices here, Crater Lake. So from Ashland, I'm going to go to Crater Lake. There's Crater Lake. Crater Lake, which was, how far away? Ashland to Crater Lake is 108 miles away, and then of course I need to return back to Portland. So from Ashland, I'm going to go back to Portland, which was 285. And I could add those all up, and there is my circuit generated by the nearest neighbor algorithm. So the nearest neighbor algorithm turns out to be so cheap and easy that a quick improvement to it is called the repeated nearest neighbor algorithm. And the idea here is that we repeat the nearest neighbor algorithm starting at each of the vertices. So let's start at vertex A. So starting at vertex A, we would go cheap, cheap, only choice, only choice. And our total cost for the circuit AD, that's not a D, for AD CBA, our total cost there is 26. That's the one we had found earlier. And that's not a particularly great circuit. Okay, so let's try again. So this time, let's start at vertex B. And from vertex B, our cheapest option is up to A, and from A down to D, and then my only option is this way and then this way. So we got B, A, D, C, B. And let's see, B, A, D, C, B. That's what, 4 plus 1 plus 8 plus 13. That's also 26. Oh, well, actually, that's exactly the same circuit we just had here. Notice that if we sort of started at B, this would be B, A, D, C, B. This is actually the same circuit. Okay, well, that didn't help much. Let's try another one. So let's try starting at C this time. So if we start at C, we're going to go, let's see, 2, 8, 13. Cheap, cheap, only choice, only choice. So we go C, A, D, B, C. And it looks like the cost of that one is, what, 2 plus 1 plus 9 plus 13 is 25. And notice that we've made an improvement now. We've found a slightly better circuit than we had before. So this is an improvement. And so we got one more to try here, so let's go ahead and try starting at vertex D. Here we go, let's see, 1, 9, 8. So cheap, 4 or 2. Cheap, only choice, only choice. And this looks like it's exactly the same circuit we just had here, right? C, A, D, B, C. Yep, so this is the same circuit. I mean, we certainly could write it as D, A, C, B, D, but it's the same circuit that we had there, so it's going to have the same cost. So this is our, so of the circuits that we found using the nearest neighbor algorithm starting at each of the individual vertices, 25 is the cheapest cost. And so this is our winning circuit. Now, oftentimes, we'll go ahead and rewrite our circuit starting at the vertex A. So we can do that here by saying, if I were to start at A, from A, I would go to D to B, from A to D to B to C, from C back to A. And so this circuit is equivalent to this one. It's just written with a different starting point. And so there is our answer for the circuit generated by the nearest neighbor algorithm, which, if you remember back, is still not the optimal circuit, but it's certainly better than the just doing the nearest neighbor algorithm once gave us. So the problem with the nearest neighbor algorithm is that it's greedy. It doesn't look ahead. And so this time, we're going to use a different method called sorted edges, or the cheapest link algorithm. And the idea here is we're going to start out by listing all of the edges in the graph from cheapest to most expensive. So here, A to D is the cheapest with a cost of 1. A to C is the next cheapest with a cost of 2. A to B, cost of 4. Let's see, C to D with a cost of 8. B to D is a cost of 9, and B to C has a cost of 13. And so now we're not going to worry about our starting location. We're not going to worry about connecting things. We're just going to go down the list here, and we're going to add these edges to our graph, or to our circuit, and unless if, so we're going to add from cheap up, so we're going to add from the cheapest up, unless if one of two things happen. So either it would create what I'm going to call a mini circuit, and a mini circuit would be something like this, where it is a circuit that does not include all the vertices. So we don't want that, and we don't want any vertices would give a vertex degree 3. So the reason we don't want that is because if we're never going to return to a city after we visited it, there's no reason to have a degree 3, right? Every city, we're going to have one in, one out, and then we're not coming back. So we don't want degree 3 ever. So let's go ahead and give this a try. So my first edge is A to D, so we'll go ahead and we'll add that into our graph. Either using a highlighter or a different color here is really helpful. So now we're done with that one. So next we'll go to AC, and we'll go ahead and add that one into our graph. Next up on our list is A to B. What would happen if I add AB? Notice now we have a degree 3 vertex, and that is bad, so we're not going to add that. This one, we're not going to, because it violates our rules here. So let's go on to the next one. C to D, cost of 8. We'd love to add that one. What happens if I add that one? Notice now we have that mini circuit. We have a circuit that it does not include vertex B, and so that is bad. I should not be adding that edge. Okay, so moving on to this one, B to D, cost of 9. No issues there, so we can go ahead and add that one. And then my only other choice is this one, the B to C, there for a cost of 13. So the circuit we end up with is A, D, B, C, A. Notice I just picked a starting point and a direction, so I said A, D, B, C, A. It would have been totally correct here also to say A, C, B, D, A. That is equivalent. If I didn't care what vertex I started at, I could also start it at B, but usually we list our answers starting at A. And there is our circuit, and that circuit ends up having a total cost of 25. Now, that's not the optimal circuit, but it's certainly not the worst one in the graph either. So this is also a heuristic algorithm. It is not optimal. Sometimes you get the best circuit, sometimes you, like in this case, you do not. But as you can see, like nearest neighbor, it is a fairly efficient algorithm. It takes a little more work than nearest neighbor, but is still fairly quick. Okay, so now let's try applying the sorted edges algorithm to our travel cost graph here. So let's go ahead and start by listing all of the edges from cheapest to most expensive. So the cheapest one we have is Seattle to LA with a cost of 70. We've got next cheapest Chicago to Atlanta with a cost of 75. Atlanta to Dallas with a cost of 85. LA to Chicago with a cost of 100. We've got Dallas to Seattle with a cost of 120. Seattle to Atlanta with a cost of 140. Seattle to Chicago with a cost of 145. LA to Dallas with a cost of 150. Chicago to Dallas with a cost of 165. And LA to Atlanta with a cost of 170. Hopefully that's all of them. And really, just so you know, I mean, you don't really have to list these all out if you're good at searching, but sometimes it's helpful to list them all out in advance. Okay, so let's go ahead and give this a try. Seattle to LA is our first edge. let's see, what was that? That was Chicago to Atlanta, right? Chicago to Atlanta for 75. Notice that these do not have to be connected yet. Everything will connect out just fine in the end. So next we've got Atlanta to Dallas. That's our next cheapest. LA to Chicago. Dallas to Seattle. And okay, we got really lucky. We're done at this point, and we have our circuit. Seattle, LA, Chicago, Atlanta, Dallas, and back home to Seattle is what we get from the sorted edges algorithm here. And this one does turn out to be the optimal circuit. We also happen to find this using nearest neighbor. So we're going to try to find an efficient circuit here between these cities in Oregon using the sorted edges algorithm. Now, the sorted edges algorithm says that we should list all these edges in order from cheapest to most expensive, and I've already done that on my paper, and so I'm going to just call them out here as we go through them. Notice that this is symmetric, so I'm only going to be looking on the upside of this triangle here, because everything down here is a mirror of that. So I start with my cheapest edge, which is Seaside to Astoria, and so we'll go ahead and connect Seaside to Astoria. And then we'll come back and say my next cheapest is Salem to Corvallis. And my next cheapests are Portland to Salem and Corvallis to Eugene. So we'll go ahead and add Portland to Salem and Corvallis to Eugene, both of which were okay to add here. Now notice something, that Salem and Corvallis both have degree 2 at this point, and so we're not going to want to visit them again. We're not going to want to add any other edges that connect to Salem or Corvallis. So we can pretty much at this point ignore any thing that links to Salem or that links to Corvallis, because we've already connected to those. So we're going to ignore Corvallis, and we're going to ignore Salem. Okay. So moving along, our next sort of cheapest option here is 78, Portland to Seaside. So we'll go Portland to Seaside, and then let's see, next is, let's see, how about Eugene to Newport. So we got Eugene to Newport here, and let's see, next one is Portland to Astoria here, 95. So Portland to Astoria, oops, and we do not want to connect that because that's going to create both a mini circuit, and we're going to have 3 edges, sorry, we would have degree 3 here. So we're going to skip over that one. So no Portland to Astoria. How about Ashland to Crater Lake for 108. So Ashland to Crater Lake. We can add that one just fine. So now we can eliminate, again, considering Portland and Seaside and Eugene from our list, because they already have degree 2, and we don't want degree 3. So I went ahead and crossed them off our list here. And so now we look for the next cheapest circuit in our list here. And the next cheapest is, I think, Newport to Astoria here. So Newport to Astoria. And now this one's kind of tricky, right? Notice why we would not want to add this. It's kind of hard to see, but it would create a mini circuit here that does not include all the edges. So we're not going to include Newport to Astoria here. How about, let's see, next biggest, Newport to Bend. So Newport to Bend, that's certainly going to be fine. So we'll add Newport to Bend. Next on our list is, looks like Bend to Ashland, which is 200. So Bend to Ashland, that's okay because we end at Crater Lake, and that should be fine. Now notice this point we're pretty much done, because everything has degree 2 except Crater Lake and Astoria, so there's only one real option left, and that's to connect Astoria and Crater Lake, and that finishes our circuit, which has a total length of 1,241 miles. if you're curious. Interestingly, this was from sorted edges. Our nearest neighbor algorithm gave us a circuit with a total length of 1,266 miles. And so this sorted edges algorithm gave us a slightly better circuit. So sometimes we don't care about a circuit or even a path on a graph. Sometimes what we're interested in is something called a tree, or more specifically, a spanning tree. The idea behind a spanning tree is that if you have a set of vertices, you want them to all somehow be connected to every other vertex. And so something like this would work just fine. This way, any vertex is connected to every other vertex, and this is an example of a spanning tree. When we have costs attached to or weights attached to our edges, like we have down here, we might be interested in the minimum cost spanning tree. And that's what we're going to try to find now. And we're going to use an algorithm called Kruskal's algorithm. And Kruskal's algorithm is very similar to sorted edges, except we're not trying to create a circuit. And so we are going to add from cheapest up. So again, we're going to create a sorted list of edges from the most cheapest to the most expensive, and we're going to add from the cheapest up, unless it creates a circuit. Now notice we have no degree 3 restrictions here, because trees don't care about degree 3. Degree 3 is just fine for a spanning tree. The only thing we don't want is circuits, because they are extra connections that we don't actually need. So we'll go ahead and we'll start here, and we'll say the very cheapest edge is this one here, so we'll go ahead and add that one. Next cheapest is here. The next cheapest is here, but notice that that would be bad, because now we've got ourselves a circuit, so we're not going to add that one. So next is down here, cost of 7. Doesn't matter that we're not connected yet. And then finally, this edge here with cost 8. Now notice at this point we're done, because every single vertex is included, and every single vertex is connected to every other one. Before we added this edge, every vertex was included, but these vertices were separated from these vertexes. It was not connected. So we need to include that. And the red graph there is the spanning tree, the minimum cost spanning tree. Now, this algorithm, interestingly, is not only efficient, as you can tell is quite quick, it is also optimal, which is quite remarkable. So this is both an optimal and efficient algorithm. It'll always give us the minimum cost spanning tree. So suppose a power company needs to lay updated lines connecting these cities to the power grid, and so they want to minimize the amount of new line delay. And so they don't need a circuit or a path, or even they don't need every city to be connected to every other. They just need a spanning tree, a way that power can get from any city to any other city. So the tree is enough to do that. So to start out, we're going to list every connection between cities from cheapest to most expensive, and start adding them to the graph following Kruskal's algorithm. So I'm going to go ahead and, just for simplicity, I went ahead and created a little ring graph of the cities. This is in no way representative of their actual locations, but it'll help me draw a graph. And so I'm going to start here with my cheapest edge, Seaside to Astoria. Seaside to Astoria here has a cost of 17. And I have the list of costs written down here, so I'm not going to jump back and forth here. The next cheapest was Corvallis to Salem, so we'll go ahead and we'll add that. The next was Portland to Salem, so we'll add that. The next one was Corvallis to Eugene, so we'll add that. The next one was Corvallis to Newport, Now notice before, with sorted edges, we would not have added this, but it's just fine to add it here because it's no problem to have degree 3 when we're talking about a spanning tree. The next cheapest edge is Salem to Eugene, but we're not going to add this edge, because if we were to add this edge, we would get a circuit between these three cities. And so we are not going to add that edge, and instead move on to the next cheapest, which was, let's see, Portland to Seaside. So we'll connect Portland to Seaside. Continuing on, the next cheapest is Newport to Salem, but that would create a circuit, so we're not going to do it. Next cheapest is Corvallis to Portland, but that would also create a circuit. How about Eugene to Newport? Nope, that would create a circuit. How about Portland to Astoria? Nope, that would create a circuit. How about Ashland to Crater Lake? Oh, that's fine. Ashland to Crater Lake is fine. How about Eugene to Portland? Eugene, where's Eugene? Eugene to Portland. Nope, that creates a circuit. How about Newport to Portland? Nope, that creates a circuit. How about Newport to Seaside? Newport to Seaside. Oh, that one's kind of tricky, but that is also creating a circuit, so we're not going to do that one. How about Bend to Eugene? Bend to Eugene, that's fine. That's no problem there. How about Bend to Salem? No, that would end up creating a circuit, so no Bend to Salem. How about Astoria to Newport? Astoria to Newport, kind of hard to see there, but it would create a circuit, so no, I'm going to skip that one. How about Salem to Astoria? No, that one would create a circuit. How about Corvallis to Seaside? Corvallis to Seaside, nope, that would create a circuit. How about Portland to Bend? Portland to Bend would also create a circuit. How about Astoria to Corvallis? Astoria to Corvallis. Astoria to Corvallis would also create a circuit. How about Eugene to Ashland? Eugene to Ashland. Oh, I don't see any issue here. Eugene to Ashland is fine, and now we're finally done. Notice that before we added that edge, this Ashland to Crater Lake connection was not connected into the rest of the graph, but by adding Eugene to Ashland, we now have a connected graph, and that is our minimum cost spanning tree with a total length of 695 miles.